Good afternoon, everyone. It is a great pleasure to introduce you today Professor Beverley McKeon. She's Professor of Mechanical Engineering at Stanford University. And before Stanford, she was from 2006 to 2023 professor at GALCIT at Caltech in aeronautical laboratories. And that's where I had the great pleasure of overlapping for a couple of years while I was a postdoc there. And she was starting her assistant professor career. And she did her PhD at Princeton University under the supervision of Lex Smith. And before that, she also did her undergraduate studies at the University of Cambridge, and then a postdoc at the Imperial College of London after her PhD before Caltech. Her area of research is in wall turbulence, and she has made contributions to the modeling of such flows. And today she will talk about coherent structures for flow modeling. She has received many awards, and that's why I need my phone up, because those are hard to remember, but definitely fellow of the American Physical Society and the AIAA, recipient of a Vannevar Bush Faculty Fellowship from DoD, Presidential Early Career Award PKs, NSF Career Award. And the list goes on without further introductions. Beverley.
Thank you, Antonino. Thank you for the very gracious introduction. It's not a good sign if you need a phone, so it means the bio was too long. Thank you, everyone, for having me here and for showing me the full Pacific Northwest weather for today. It's been a beautiful day, having come up from the Bay Area. It's been, I think, what did we decide, maybe 7 years since I was here last. I did look back at my slides, and some of what I will say will be an update on something that was tentative. I think we were sort of forming some of the ideas behind this some time ago. And some of it will be a little more data-driven. And so the underlying themes here are, what is a coherent structure when you start to think about modeling for turbulent flow? So everyone will be able to think of ways to identify a coherent structure. This is the variety that might be useful for understanding flow next to walls, specifically at high Reynolds number. So thinking about large aircraft, large ships, submarines, those sorts of things. There's plenty of funding sources that have all contributed to this. So I tried to synthesize a few ideas. I'm sure I showed this slide last time. I won't spend too long on it, apart from to point out that as you move towards the right on this plot, as you increase your Reynolds number, you're moving from the sort of things. Do we have a pointer? I didn't. Oh, I do have a pointer. I do have a pointer. There we go. Okay, here we go. From the sort of things that we see in the laboratory, this is a pressurized set up, the super pipe at Princeton. Now we're moving into the industrial realm and all the way out to the atmospheric boundary layer. So why am I showing this plot? Just to give you some sense for the scales involved. And again, this is an old one. Apologies if you've seen this before. In this facility, this wind tunnel facility that I used to operate at Caltech, boundary layer thickness is about the diameter of a golf ball. There are coherent structures, very long structures that are about 2 basketballs in length. And the viscous scale, the smaller scale, is about the diameter of a red blood cell. So even in this laboratory scale facility, we need to span that wide range of scales. And then if you took this super tanker, stood it on end, it would be the height of about the Empire State Building. The 2 basketball length is about a 2-story building in height. The boundary layer height is about as tall as me doing this, and the viscous scale is a fraction of the diameter of a human hair. So the reason to need to do this sort of thing is that even with the best computing power, and gradually all of these arrows move out towards at least the computation ones move out towards the right, we need to do something to understand, to reduce the complexity of the range of scales that are needed in both space and time. And so here I'm showing you only the spatial scales, as well as it being a fundamentally interesting question. So for today, also another old picture that's sort of a concatenation of things that we knew or know about wall turbulence. So when I started out as an assistant professor, one of my goals was to say, we know all these things. Is there some way that we can understand all of these rather than saying one is right and one is wrong, to say they're all observations of the same system? How do we understand it? So today I'm going to talk to you a little bit about how we can identify coherent structures. Some of the Some of the simplifications that come with moving into space-time instead of space or time, which is historically where we have measured, and then show you that there are some simple origins for things that we've spent a long time identifying as coherent structure once you're in space-time. Understanding what that means with regards to modeling, with regards to nonlinear forcing, and how turbulence sustains. So will I actually tell you how to model at the end? No, but hopefully I'll tell you that we're making some progress towards new ways of thinking about it. I'm going to use modal approaches really as a way to break us down into space-time. It has some linear connotations, of course, but there's a large literature and there's a lot of great work come out of this school in particular through several of the groups. So if we have a data set, if you like, was it the data-driven piece that said, no, I'm sorry, I shouldn't make any jokes. Right. So if I have the answer already, if I have the data set, how could I compress and extract some important things from that data set, given these wide range of scales? So here are various techniques that you might employ, whether you're trying to think about the evolution of the flow or really just try and capture things that are the most energetic. So that would be the POD and SPOD. Why did that go away? There we go. In some sense, this one is an older topic, so starting with the equations, but it's come back into focus really with the connection to the data-driven piece. So as data has become more available, data-driven techniques have come to the fore. The equations we've known for a long time, but we have different ways to analyze them. And for today's talk, a really important thing is that if I call the equation-driven approach resolvent analysis, and I think about the spectral proper orthogonal decomposition, so one data, one equation-driven, there's some really nice work from Aaron Town. I killed that. Really nice work from Aaron Town that shows that the modal basis, so the way of deconstructing the flows both from data or from the operator or equations, actually will be exactly the same if the nonlinear forcing in the system is white noise. So if it's uncorrelated. Now we know that's not the case, but at least it tells you that both methods will give you some basis set that should be useful, whereas one you will get if you already know the answer, the other one we want to use to get towards the answer. So we're going to work from this basis. I can give entire talks on the resolvent modeling framework. Today it's a tool where we'll use the basis sets to understand some of the origins of turbulence structure. So in short, we take what's called a Reynolds decomposition. So a mean field here, we take the instantaneous velocity and pressure. I'll work with incompressible flow in a Newtonian fluid. For today, you can do other things. So I'll take the instantaneous fields, decompose them into a mean, and then the fluctuation. And if you do that over here, the red terms are somewhere that nonlinearity has been active. So this U is the turbulent mean. It's not the laminar or the equilibrium solution. So that's been moved away from the laminar solution by the action of the nonlinear terms. And this term is explicitly nonlinear in the fluctuation. So then we take this and we reorganize it. So in schematic, I've just taken those terms and I put everything that was linear in the fluctuation here, nonlinear forcing up here, or nonlinear terms up here. And we think about that nonlinear forcing as exciting a linear set of linear dynamics here that are governed by the operator, the transfer function that's called the resolvent. Importantly, that turbulent mean field that was in red on the previous slide is an input here, so you have to know it. But of course, that's the easiest thing to get with a Rand solution or an eddy viscosity or those sorts of approaches. What we're interested in is the fluctuations and how the turbulence self-sustains. So this type of figure has been drawn many times. So if I cut off the top part here and I just kept the green, I could think about this as a stability analysis, right? So under what conditions do I get an unstable behavior of the linearized Navier-Stokes equations? It's been framed in terms of an initial value problem or transient growth. People have looked at continuous forcing for laminar and for the laminar base flow in particular, and also for the turbulent mean. But we did some work that actually said, well, rather than try to work out what is the forcing that gives us turbulent-like behavior, let's analyze this system as it was for the equations that I showed you, in which we know what that forcing of the linear operator is. It's exactly this nonlinear term. And so I could write, well, let me slow down. So I know what that forcing is. So let's look at this whole system. So for what we'll look at today, I'm going to focus on a channel flow. We can do this for spatially developing flows. There's a reason to do this in terms of this parameterization. So we'll parameterize in homogeneous direction. So kx and kz are the streamwise and spanwise wave numbers, and omega is the temporal frequency. So we're assuming a flow that is periodic in the streamwise and spanwise directions and homogeneous in time. And I'll denote that by this bold k. So once I'm in that parameterization, I can write what's going on in the green box in terms of a velocity or a velocity and pressure response as some transfer function, the resolvent acting on the forcing. And the forcing is some nonlinear function of all the other k's, right? So we know that it's a quadratic interaction. We know, I'll talk a little bit more about what possible scales can interact through this nonlinear forcing. So that's the full problem. There's no modeling here so far. The modeling comes in saying that we have learned, I know quite a bit about this resolvent operator. I can do a singular value decomposition of that to give me the left and right singular functions. I can think about these as the response to a given forcing weighted by the gain for that particular forcing. So the first singular mode will be the one that gives me the most amplified response with an amplification factor of sigma 1. Once I have that decomposition, I can write my broader velocity field in terms of an expansion in those modes. I could do the same with the forcing. These chi's that you see here are the weights. So everything I did so far is just determining the basis functions. To close this loop, I need the weights, how much of each basis function I have. And so the goal here is to truncate this, to say, well, how many of these modes do I need for a given k, and how many of the k's do I actually need, first of all, to approximate turbulent structure, second of all, to approximate it in a way that is useful for turbulence modeling. So what are the important modes under some metric? However, for today, I'm going to use this as a way to get a basis set that we can use to see what gives, what leads to some turbulent structures, and then we'll go into a data-driven approach to actually look at the content of the forcing. So what do you get if you take a look at some resolvent modes? So I'm going to take the first mode in the J expansion. These are the first singular modes. And I'm going to take left, and you should think about these as oblique traveling waves, right? If I've taken an SVD where I have a Fourier decomposition first in x, z, and omega, these are oblique traveling waves with some dependence in y. So I'm dealing with the Hermitian symmetry and doing left and right traveling waves. And so these are isosurfaces of each velocity component and then of the shear stress associated with that. So you see that the U and the V, sorry, U and W have some inclination in the streamwise direction. Flow is in the plus x direction. V sits very vertically, so there's no phase variation. And UV we'll come back to a little bit later. But that's an example for one type of mode. What's interesting about going into space-time, so I didn't stress it, but by going into wave number frequency, we're now in space-time. What's interesting is that the response, the Y variation, is localized around the critical layer. So I can tell you, if you give me a kx and an omega, where that mode is going to sit in the flow. And so these, in this picture here, these dashed lines are critical layers, so that's where the wave speed is equal to the local mean velocity. So omega on kx is equal to the local mean. And this is for a fixed kx and kz and increasing wave speed, so increasing omega. So these are 3 different wave numbers. So the blue ones are the small ones. You can see what happens as you increase speed. They tilt over, they lift off, and they continue moving away from the wall. Same with the gray. The red ones are going to have a special significance as the last ones to lift off from the wall. All right, there's a kx that's the last energetic wave number that actually detaches from the wall and moves away from the wall. And 2 things that we'll need a little later is if I look at these modes, I'll talk about scaling with distance from the wall. And so if I think about this blue mode or everything here, I can talk about the height of the mode as being proportional to distance from the wall. Okay, so it touches the wall, and then it's sort of roughly twice the height to the critical layer. So that's one way to scale with distance from the wall, where that factor is 2 times the distance to the critical layer. Out here, I can still scale with distance from the wall. I just don't have to touch down to the wall. So the constant in front of that could be, say, a half, right? So say this silver one is, this distance is about half of this distance. So there's 2 ways to scale with distance from the wall. So that's what happens as you go up in wave speed. And again, the fact that we know where this response is localized in y is something that you get by going to space-time. Now, the other thing that we will use in passing is that these mode shapes turn out to be very simple for the channel flow. In fact, you can approximate them by a Gaussian in the magnitude for this I'm going to show you for the streamwise velocity. So a Gaussian in magnitude where the peak is at the critical layer, and then a linear variation in phase. So that's what gives you that tilt. Okay, that's a linear variation in phase. So that's some work that Scott Dawson did when he was a postdoc with me. So all of this preamble is to say that we have a proxy for mode shapes in turbulent flow, and now we're going to see what that can tell us going forward. I want to stress, however, that each of these pictures that I've shown you that are stationary are associated with space-time. So if I take 3 modes from above, and I convect it, they're all convecting downstream, right? I can't see much of a difference here, but if I sit in the frame of the green modes, clearly the red one, the ones higher up are moving with a higher wave speed, and the ones lower down are moving slower and therefore appear to be moving backwards. So this becomes important later on. In fact, I'm going to skip to that and come back to this. So here is some streamwise velocity data from an RE tau 1000 simulation in DNS. So from the time evolution, everything looks very complicated. And it is. I would be wrong to tell you that it's not complicated. But based on what we were just looking at, we already know that there are some different wave speeds. There are things moving over the top of each other. So down here, we've restricted that. So this is for wave speeds that are associated with a critical layer here or lower. And so perhaps you can already see that, you can't if I leave the cursor there, perhaps you can already see that we've already got something that's coherent sitting within a much more complicated picture that we can get a handle on more cleanly because we filtered by wave speed. So this picture, if I get time, I'll talk about a little later on, because this is our target now for a wall model for large eddy simulation, because we know a little bit more about this structure and how to model it. So space-time important. The other thing that's important, and the thing that I skipped over, is here. So the input to the resolvent analysis is the mean field. And for the channel flow, again, we already know a lot about this. We know a lot about the self-similarity of the mean profile. In fact, I spent my entire PhD working on the scaling of this for high Reynolds number. And decades before and since, people have looked at this. So with distance from the wall, so this is a semi-log plot, we know that we have a linear region, we have an inner scaling region, which means things scale on y+, so scale on the viscous scale. There's an outer region or a wake region where things scale on the outer scale, so h, the half height for the channel. So that's this y is normalized with h. And then in the middle, there's a sort of spanning region where everything depends on distance from the wall. We call this the self-similar region or the logarithmic region. So as you go up in Reynolds number, the outer and the inner regions pull apart in y+, and this log region grows. It's like a buffer between the two, where both inner and outer scaling hold. So if we already know this, this self-similarity will be impressed onto the resolvent. And in fact, you can define wave numbers and wave speeds where the resolvent operator will be exactly self-similar because the mean velocity is self-similar. So without sort of boring you with all the details, you will recover that the wave length here will scale with the viscous unit. So for lambda x plus constant and c constant, you will get the same operator. You can say what happens to the SVD as well. In the outer region, you have a particular scaling. And then we'll talk some more about what happens when the velocity is logarithmic. It turns out to be a very specific condition. So again, we can use the fact that we know several things about the inputs to the resolvent to extract some additional modeling information. Okay, this is a sort of modular talk, so I'm going to stick with the sort of more interesting ones. Let's go straight to the logarithmic region. So let's talk about first the footprint of spatiotemporal mode. So this is the mode I showed you before. And this is what happens if I add that mode, where blue is the negative streamwise fluctuation associated with that mode and red is the positive. And this is the 2D cut, so streamwise and wall normal. And this is the 3D isosurfaces associated with that. And the black line there is an isovelocity surface. Not quite sure. Oh, there we go. I see that my axes have sort of jumped over. Sorry, these axes are associated with that image there. Now, if I add in the mean profile, I'm going to see this type of effect. Okay. So even though I have something that looks very symmetric, right, about the critical layer here, when I put in the mean, and I haven't specified the relative magnitudes of these for right now, so this is an example only, but I end up getting these bulging structures, which look like this in 3 dimensions. So this is the deflection of an isovelocity surface, isovel. It goes up in an asymmetric way to the way it goes down because I have a shear profile in here. Right? So this is just what happens when you sum these two. Those of you who've looked at turbulent flows will recognize, at least see this some familiarity in the sort of turbulent bulges that you see a lot in wall turbulence. So again, without specifying the relative magnitudes, that kind of bulging shape has a very simple origin in the type of mode that has, in this instance, a Gaussian amplitude variation and a linear phase. Right? So you get that bulge as a natural outcome. Now, we also get hairpin vortices very cleanly. So if I look at the U's and V's there, I can sort of see that if I have an up V, and if you look at the spacing of each mode, you can see that there's a possibility at least that you have a low speed streak coming this way, and you have the U and V such that if you put the U and V together and then the W together, hopefully you can see, if you do this, I guess it's really a sort of fluid mechanics class question, but if you put those together and I look at connected vorticity, whatever measure I want to look at, I will see these connected vortex structures arranged such that the rotation on the head is such that there's a low speed streak between the legs of this vortex. So again, just by looking at one mode here, I can produce hairpin-like vortices, which are also observed in turbulent flows. But this is for one mode. If I put 2 modes together and do the same diagnostic, I can see something a little more complicated. And if I put 3 together, as I've shown here, so they all have, in this instance, they all have the same wave speed, I have something that is a lot less clean than this, clearly has hairpin vortices and remnants of hairpin vortices, and something that we would call a packet, so they're arranged in a streamwise direction. So the difference here and in the one before is that we've gone into space-time, and so we've looked at for our coherence in the Fourier domain, whereas almost all of our observations are in the physical domain. And the way we diagnose structure in the physical domain is typically based on a conditional average. So this is work from this very nice Dennis and Nichols paper from 2011. And so what they did was look at 3D PIV images, and when they saw evidence of a hairpin vortex right here, they averaged the flow around it. Okay, so you're waiting to see this structure, and then you're seeing what the flow around it is. And so they saw a low-speed streak between the legs, high-speed streaks either side, and then they were able to see also this sort of inclined packet of hairpins as well. So this is sort of fundamental to describing what I'm talking about as a different way of thinking about coherence, because in space-time, things are very, very clean, right? In the physical domain, they're very messy, and we try to recover the cleanliness, if you like, or recover the structure by conditional averaging. The trick, of course, is that if I look on the left-hand side, I never see those fields. I especially never see those fields because there's so many of these modes and they're convecting over each other, and my eye can't pick them out, right? But similarly, if I look on the right, I can't pick out that there was a modal origin, or at least a modal representation, I should say, of these things. So this is the different definitions of coherence that I'm using for today. Okay, so now let's talk a little bit more about the spatial footprint of self-similar structures. So this is from Valikivi et al. And I'm going to introduce a slightly different definition for the mean velocity. So these plots are, this is actually for a boundary layer, for increasing Reynolds number, going from left to right. The open symbols go to the right-hand axes, and those are the mean velocity. The filled symbols go to the left, and that's the streamwise variance. And up here you have the spectra associated with the streamwise velocity spectra, power spectra associated with this distance from the wall. So the point of this paper was to, well, you can probably see it, is as I move to the higher Reynolds number in this blue region, I can see the log in the mean that we've already spoken about, but there's also a log in the variance. Okay, so over here, can't really see it, the blue curve is bending over. Here you might say, yes, I could probably fit a tangent curve here, but here, very definitely, there's a logarithmic curve in both. And so these authors split up, rather than saying that there was an inner region, a log region, and an outer region. They said actually there's two. There's one where the mean is logarithmic, but or at least they say there's a very tiny region where both are logarithmic here. So there's green, just the mean, blue where both are, and the blue one is the one that grows faster as I go up in Reynolds number. And so this is what the various proportions of the boundary layer height look like as you go up in Reynolds number. So question is, can we understand this by thinking about the structures in the flow? And the reason that these authors were particularly pursuing this approach is that if you take what's called the attached eddy hypothesis and you deposit arrays of hairpin vortices, the geometry doesn't matter too much, but you deposit them in a way that their dimensions all scale with distance from the wall in either sense that we were talking about. So you put in some hierarchies of red vortices. The maroon ones are a bigger copy scaled by distance from the wall, and then the black one are scaled again by distance from the wall. You recover exactly these two log laws. Okay? If I superpose these on a uniform flow, these attached eddies, I get back these variances. So the question is, why are there two of these regions? So let's go forward. Right, in terms of the resolvent modes then, this is what happens close to the wall in the inner scaling that I skipped over. So as long as I keep y plus constant and then the wavelengths constant in plus units, everything looks the same. As I move further from the wall, there's what's called a mixed scaling region. So here's that red mode, very tall one that reaches down and touches the wall. Here are some modes that vary from touching the wall to detached from the wall, but there's also a set that are all detached, right? So if I go far enough from the wall, everything has detached from the wall. And I'm going to talk a little bit about the blue ones specifically in a moment. But there's a difference now between the regime where some of the modes are attached to the wall and everything is detached from the wall. So some of them have the one factor in scaling of distance from the wall, and everything does not have that schedule. Now, these blue ones are very specific. They are geometrically self-similar. So if I have a logarithmic mean profile, I can define families of these modes such that if I know what's going on at one particular wave speed, I can tell you exactly what the mode shapes are going up this particular scaling, and this tilde scaling, which I've lost here, let's go back here. Tilde scaling is, hat scaling is these two. So lambda z would scale with distance from the wall, but lambda x scales with y plus instead of y. But if I obey this scaling, then I can tell you from one of these blue modes all of the ones in this family. It's a consequence of a logarithmic mean profile. There's a collapse of the modes just to show you that it's true. And then I won't have time to talk about this here, but there's a really strong consequence of having modes that are self-similar in y and across Reynolds number. And if I look at the spectral transfer and transport, then I can talk about the production, the dissipation, and the transport being self-similar on a hierarchy. So if I understand it at one Reynolds number, I understand it at all Reynolds numbers, which is a very strong statement. It's not to say we understand it yet, but if we did, then we would be able to leverage that at different conditions. So let's look at what happens on a hierarchy. So here I've picked, it doesn't really matter which one, it's got 5 members of a hierarchy. It's a relatively high friction Reynolds number, 15,000. And I obey this rule. So the next member in the hierarchy sits at twice the height of the original one. There's 5 members. And this is an isosurface of the negative fluctuation. It should be blue, it's in red, of the negative fluctuation. So let's zoom in on one little section of it. And maybe you can start to see why I call this geometric self-similarity, right? If I look at the top, the big structure, it's a carbon copy of the next layer down, a carbon copy of the next layer down. And in fact, we can color code these. So we can say the green one is the big one. It has 5 members in it. It's a fractal type behavior, right? It has the same thing repeating 5 times. Blue has 3, yellow has 2, etc. So we're going to use these now to understand a little bit more about the origin of some complex structure in turbulence. So here's some Here's some experimental data. So this is a PIV window. It's a narrow window for a reason that will become obvious in a moment. This is the full boundary layer height, and we're looking at the streamwise velocity. So if we were looking at the mean flow, I would expect to see a monotonic change in value, right? This is what I see instantaneously, and your eye should be drawn to regions that have the same color over extended patches in Y. So several people have observed this going back 25, maybe 30 years at this point. We call these uniform momentum zones. So how do you observe these? Well, we take a narrow window and we average over it and see, or rather we count the instances of a particular velocity being observed and then average. So over here, this is the value of the velocity normalized by the free stream. And this is the probability of seeing that value. So in this static version, you can see that there are very definitely 3 regions of almost uniform momentum. Okay? If this were, I'll show you an example in a moment of what would happen if we had just seen the turbulent mean. And then as we were playing this, you could see that these values were moving, and so actually were the number of peaks. Okay, so there's 2. Right, and then all of a sudden that third one picks up. So this is the probability distribution associated with what's going past the window. So these are called uniform momentum zones. People spend a lot of time trying to identify these, to bound these, to count them, to see how they vary in time and space and with Reynolds number. So what I'm going to show you now relates to a simple origin for these. So we were just looking at this 5 hierarchy structure before. Now I have the plus and minus fluctuations. These are the 5 critical layers, and this is to show you again that they're evolving in time. So the top ones are moving faster, the big ones are moving faster than the slow ones. And again, if I add in the mean, turbulent mean, first thing you see is that bulging that we saw happens across scales, right? So now we have something that would look a lot like those uniform momentum zones. Too clean, because I only have one hierarchy in here as opposed to thousands of different modes. But I have something still, and it was evolving, that has at least the same type of behavior. And I want to play this one again, because if you look really closely, there's something interesting. Because the top one is moving faster than the other, the structure is always self-similar, but it actually evolves a little bit, right? Because this one is moving faster than this one, etc. So it's any instant it's self-similar, but it's a little bit different. Okay, so again, just by resorting to things with different wave speeds, we see things like bulging, hairpin vortices, we see these uniform momentum zones. And this is what the PDF that I was showing you before would look like. The blue one is for just the turbulent mean. This is exactly what the equivalence, just rotated, of what we were looking at for the PIV data. So with a 5 hierarchy setup, I see 5 of these peaks, right? They're very clean, again, because I only have one hierarchy in there. And then over here, this is what would happen if I plotted the instantaneous velocity on the axes I showed you for the mean. And I'll play it again, but if you watch these red steps, so anything that's flat here corresponds to a region of y that has effectively constant momentum, uniform momentum. So that's an exact analogy to the uniform momentum zones. And if you watch closely, you'll see that these move downwards. They move towards the wall. So let's play that one more time. Okay, so you see each of those red wiggles moves down towards the wall. Okay? You don't see that unless you look in space-time, and you see it very cleanly with these hierarchies. The punchline is it's a consequence of these streamwise inclined structures passing this point, right? They pass high, and then they come through lower. But once you have this sort of template to see it, you can understand why that's the case. Can we model it? Yes, we can. So here are instantaneous snapshots of the PDF plotted out in time. And that's what this is showing. So here's the time dimension. Here's the U scale. And so these phenomena are exactly that, moving down in U, moving down close to the wall thing. So this was an observation from experiments, and it's the first time that we're aware of that people had looked at this. So Angeliki Laskari looked at this, understanding the time evolution of these uniform momentum zones. And then she said, well, I wonder whether we can model these. Where has that gone? Well, what should be there, and I don't know why it's gone, is this picture. So remember those streamwise inclined things. Here's what you get if you put in just this one basis set with this streamwise inclination. If I put in my full hierarchy, I start to see a branching structure, but still with that same inclination. So I'm not saying that this is what you see in a flow. What I'm saying is that these very complex scenarios that you see have a very simple basis. They just have very many of these things overlapping with different spatial scales and different temporal scales, different wave speeds. So I'm giving you a template, if you like, to understand some of the more complex scenarios. So one thing I'm interested in doing is sort of parsing all this out to say, well, what does this mean for this picture? And I've spoken about it at some length. So there's a regime where there are things that are physically touching the wall, attached to the wall. There's one where everything is detached. There's one where we know the inner scaling. And this kind of scaling is very important for understanding how to populate the near wall region for a wall model where that the y plus value where you put your interface will vary with Reynolds number. All right, let's spend a little bit of time on the VLSMs, the very large scale motions. So in these plots, I can't reach from there, in these plots of the spectra, this is the inner peak, the near wall cycle that a lot of people have studied for a long time. Out here is a secondary peak that only becomes very clear as you go up to high Reynolds number. So during my time as a faculty member, these things have been identified, characterized, and there's still some debate as to their origin, but their importance, I think, is beyond doubt. So you only see them at high Reynolds number. These are the two basketball effect, or the two-story building coherence in the streamwise direction from the beginning of the talk. What's really interesting about these, there's a series of very influential papers that summarize very well in this Marusik paper, is that if I take a signal, this is one from close to the wall, so a temporal signal attained by a hot wire. If I do a temporal filter to separate the low frequencies from the high frequencies, or the large scales here from the small scales, they sum to give you this, hopefully you can see here in this very nice picture that there's a correlation between the envelope of these small scales, or the magnitude of the turbulence activity, that seems to be modulated by these large scales. Okay, so you would say that's a nonlinear effect. There are large scales here that are having an effect on the small scales. Good. You might even say close to the wall that if a large-scale positive excursion goes by to a little eddy close to the wall, that feels like a higher Reynolds number, so it gets more energetic. That would be good, except for the fact that if I move away from the wall, this effect reverses. So instead of getting higher activity with a positive excursion, it actually suppresses far from the wall. So what's going on? Well, in our super simple modal world, this is an effect that has to be present, right? So if I take 3 modes, and I'm going to introduce this plot that I'll use later. So this is a la Feynman, a Feynman-type plot. So if I have the interaction, nonlinear interaction of a mode with Ka and a mode with Kb, I can only get a resonant interaction such that I have a K of Ka minus Kb. Right, that's the resonance condition. So remember, this bold K covers Kx, Kz, and omega. So there's 3 conditions written into this. So I'm going to take, for now, let's just look at the x ones. So let's take 7 minus 6 equals 1. So here's just a spatial representation where the black is the large scale, red and blue are the small ones, very close together. And you can see in this very simple world, it's just beating. Right, it can only be just beating. So the 7 and the 6 are very closely aligned, as I've drawn them here, with the large amplitude, and then they're almost out of phase with the small amplitude. If I add them together, I see exactly that, right? There's a large scale peak and a lot more activity, and vice versa. However, I can move around the sense of that interaction through the phase of the small scales, right? So here's one where the envelope is aligned with the positive peak, but I can move these in the small scales relative to the large scales. So again, if you think about an assembly of sinusoids, essentially with different phases, different amplitudes, different wave speeds, I will always see this type of effect if I look at any 3 modes. If I see it in the full signal, it's in some sense a representation of the very large-scale motion, the Kx1 mode being energetically dominant, which we saw in the spectrum. Has a little bit more importance because it actually talks also about, there's some information there about spectral transfer and spatial transfer of energy. And then just to remind you again that even though I've shown you the static pictures, everything here is convecting. And although it looked like everything had the same wave speed, that's actually not required. All that's required is that the envelope of the small scales has the same speed as the envelope as the large scale. Okay, so what? Well, I would like to be able to predict that relationship, and especially that reversal of phase from the wall to far from the wall. And it turns out if I use this very simple Gaussian amplitude with a linear phase variation, I can do that. The question is, the resolvent analysis I introduced at the beginning is exactly wrong for this, because I want to put the u as the input and get something about the r, whereas this one was set up the other way. But I can still think of a transfer function type relationship, and to do that I can use the Reynolds stress equations. And after the worst math of any paper I've ever done, and it took 10 years to get this out the door, and I'll show you why, Ian figured it out. And if you do this transfer function analysis, you find exactly what I said, which is that the large scales are sat there in the background. These transparent ones are the envelope of the stress, and they are inclined in such a way that they're in phase close to the wall and out of phase far from the wall. So why did it take so long to get the paper out? Because unless you're really careful, you get exactly the wrong phase. So there's 2 ways that this could happen. One is with that inclination, and the other is with that inclination, right? And it turns out you have to do a viscous analysis to get that one. If you do it in viscid, it comes out that way. So there's kind of a lot of stuff there that I'm going to skip in the interest of going forward. But again, it's to tell you that in this modal representation, this very complex thing that we spend a lot of time diagnosing is encoded there. It must be. Comes out of the equations. Okay, with the remaining few minutes, I want to talk now about a data-driven study of the structure of the nonlinearity. So I've told you about some simple origins for coherent structure that might be useful for modeling. So that's for the linear part of this analysis. Let's see now if we can say anything about the nonlinear part. And so in broad brushstrokes, if I take two modes, here we call them psi A and psi B, I've told you that we're looking for resonant interactions. So I take the nonlinear interaction of these two. This is just a schematic version of what these would look like. And they can only give me the Ka plus Kb in this instance. And a particular nonlinear interaction will give me a forcing, right? That's true. But not all of that forcing will be equally amplified through the resolvent. And one way to think about that is how that forcing projects onto the singular mode. So I could follow that path and project it onto many. The other thing I can do, which I'll do next, is just run it through the resolvent and see which ones give a large forcing, which ones give a large response, and which ones give both. OK, I'll skip that bit. Right, so here's what we're going to do. We are going to break down the forcing at any wave number K3 into all the contributions from resonant K1 and K2. And I will draw a distinction between when that wave number sits in the U or when it has been operated on with the gradient. Okay? And if you think about this, this is going to make some sense because a big mode here, a big energetic mode here might make a big contribution here, but might not make a big contribution in terms of the gradients. Right? So it is important to maintain those two. So schematically here, we're going to look at all of these interactions and how much they contribute to F. And then we're going to run that F through the resolvent operator, one more, and see how much each of those contributions contributed to the response. So this is probably the worst visualization problem we've ever had because we've got a four-dimensional space and then we're looking at every possible triadic interaction. So to save us, well, hopefully to save you a headache, to save you a worse headache, we're going to integrate across kz and omega and in y. So I'm going to show you plots that are associated with the interaction of different kx's and how those drive the forcing and how those drive the response. So P will pertain to how much forcing is contributed and R to how much response. So we do this using DNS data, this time at an RE tau of 550. You have to be careful because as you window it, you actually can accidentally end up introducing additional forcing. That's been covered by Noguera et al. So careful data analysis. So here's the key plot. I'm going to walk you through it. So the first thing to say is that on this axis is the K1. So that's the one that sits in this seat here. K2 is the one behind the gradient here. And this is it's a logarithmic, it's not a linear scale, it's a logarithmic scale. But dark here corresponds to a large contribution to the forcing. These diagonal lines, let's go back one, here correspond to constant K3. All right, so 0 and 0 will give me back a 0. A plus 127 and a minus 127 give me back a 0. So diagonal lines are for a constant output, K3. These are large scales, close to the 0, going to small scales, and these are the resolution limits of the DNS. So up here, we have small to small interacting, get this right. Yeah, small and small interacting to give us a low K3, right? I've got a plus high number, a minus high number, so I get a low K3. Over here, I have large and large giving me large, all right? So you can understand various features of this plot. However, hopefully what jumps out to you is that there's a very strong region here. There's a line kind of fainter there, and there's a little diagonal line. It's kind of hard to see, but there's a concentration around here. And what's interesting about that is that these two, the horizontal and the vertical line, are always associated with a kx close to 0, so a very large mode. And the diagonal line is the self-interaction, the mode with the negative of itself. So there are three things that my eye would pick out as being important in terms of the interactions that contribute to the forcing. Now let's look at the response. So same type of plot, same explanation applies. Let's put them side by side. And you can see that there's some similarities, but there's also some differences, right? So this whole region that was giving me a large contribution to the forcing gives me some contribution to the response. I can still see those, just about see those 3 lines, but there's clearly something going on here that really didn't do much in terms of the response, right? So I skipped over a slide that showed that we could actually do a Helmholtz decomposition of the forcing to split out the bit that actually sort of does the damage versus the bit that can be wrapped up into the pressure. And so really this plot tells me that although a lot of concentration is on modeling the forcing, there's a portion of that that even if I get right, it's not going to change this response piece over here. It'll come into the pressure, but not through here. So now I can be a little bit more precise about which are the dominant interactions I want to keep. And I would say if I was wavering about these ones, I should definitely keep these. And this one stays the same. This one perhaps not so important. And then one last comment on here, which again is a talk of its own. There's a technique called quasi-linear simulation or restricted nonlinear or 2D 3C simulations. And in those, anything with a kx of 0, a streamwise constant mode, is resolved. It's kept with the mean. And then any interactions with that mode are kept, and any ones that are small scale to small scale are modeled. And under that, the exact interactions that are kept are these green lines here. So hopefully you can see that even in this this is an asymptotic analysis to get this timescale separation. Even in this 550, not particularly high Reynolds number flow, you can see the imprint of these same interactions. There's a lot more we could say here, but as you start to resolve more and more big scales, you start to keep these blue swathes instead of the green line, and then there's always some red bits that you don't get. So we can sort of see why QL has some success and how you might improve it from this model. Okay, so I see like 10 till, so this is a good time to finish. So the summary. So sometimes I wake up and I'm like, oh, this is all really trivial, right? Because it's all sines and cosines. It's all from an SVD of the linearized operator. But the point that I would like to make here is that, first of all, space-time is something that we can access now, and there's folk in the audience who both model with it and use diagnostics that obtain space-time information. It's crucial. We didn't used to be able to get a hold of that. We used to be able to get one or the other. That's changed during my time as a faculty member. But there are a lot of things that become simpler to see if you can go into the space-time domain. And in fact, I would argue that you can define coherence in a different way if you can get into that representation. I've shown you that phase relationships between these spatiotemporal modes are important. There's another piece of work that I won't have time to talk about today, but we'll present at APS, that actually predicts some of these phase relationships on a mode-by-mode basis and shows that they're very tightly constrained. So there are only certain ways that modes can go together. And if you put that information together with what we already know about spectral scaling, there's at least something very tempting to pursue that's out there in terms of how you predict how turbulent flow will behave. And then we've gone in and characterized the nonlinear interactions and shown you that there are potentially some compressions that you can have there once you go into space-time. I'll talk a little bit more about this one because I introduced it. So once we have these types of self-similarities and a way of trimming the wave speeds that we look at, we think that these types of arguments should be able to inform both LES wall models, but also reconstructions. So a lot of the wall model approaches give you a way to get the mean velocity correct, but don't give you any eddies or any fluctuations close to the wall. And so by putting in some principled way of putting in resolvent modes and scaling them up, you can actually get some pretty good representations of the turbulent kinetic energy and the wall shear stress fluctuation. So that's with Ugo Piamelli at Queen's. I want to end with 2 quick advertisements. So the first one is Physical Review Fluids, is the journal of the APS Division of Fluid Dynamics. I have the privilege of being one of the lead editors of that with Eric Lauger, chief editor, Eric Lauger from Cambridge. Here are some highlights from the journal. We particularly welcome your submission of discovery for fluid mechanics, and we'll actually be announcing a new section that deals with novel methods that enable fluid discovery at the DFD meeting. So we'd love to see your work coming this way. And the last one is I've got too many hats, so take off the researcher hat, take off the editor hat. But I also work at the Center for Turbulence Research. This has been funded by the Office of Naval Research from the directorates covering air, sea, and geophysical fluid dynamics. And so there are some really good opportunities there for postdocs that are sort of a halfway house between a postdoc where you join somebody's group and one where you're sort of working on your own or you're an assistant professor. So you write a proposal, it's competitively assessed. If you're successful, you come in, you can work on that topic, you can work with your colleagues, put together pieces, your thoughts, your expertise to create something that's bigger than the sum of the parts. You're mentored by any or all of the faculty associated with CTR. So if this is something potentially of interest, the information is all here, but please come and talk to me. I'd be delighted to welcome some new folks applying to the university, to CTR. So with that, I'll finish, and I think I've left a little bit of time for questions.
Thank you, Beverley, and let's see if we have questions in the audience. Please go ahead.
A lot of that went way over my head, but what do you see as the most interesting application of your research used in industry or in
Yeah, so I think that this thing I touched on, and Ugo at the DFD meeting will talk solely about this, is potentially the most powerful tool. So there are places where LES wall models will struggle, and they're known, so separation is there are experts in this in the room. And some of that is to do with the fact that, in an LES you will put a grid point, your first grid point, far from the wall, and it would be way above, actually, go all the way back up to that first movie. So, oops, I get there. Yeah, here. So everything. This might be your first grid point at point 1 in the channel. So everything below this, all that space-time dependency that you're seeing gets lumped into a way to basically impress the wall, get the right wall shear stress. Right? So there are no eddies in a typical LES wall model here. So that means you don't get any of the motion. You couldn't think about particle transport. You can't think about extreme wall shear stress events, anything like that. So that's one thing I'm particularly excited about, and it actually speaks to a criticism of this type of work that goes back a way, which is that we spend a long time identifying coherent structures, but what have we actually learned about it? What do we do with them, right? So we do spend a lot of time spotting them and finding them and being like, yes, I can describe it, but then how do we leverage that? So, my particular take would be to say, I want to identify them in a way that can be useful, and it can be useful both in terms of eddies here, so fluctuations, but also in terms of what would give you a minimal self-sustaining representation. So how do I plug this into a code to get more out of it than we currently can? What we hope is that by putting something universal in and maybe scaling it, as I do this with a developing boundary layer or a pressure gradient flow or something like that, I can bake into it enough of the physics that it's useful beyond the channel, right? So I want to see when it breaks is the right way to say that. So that's the first thing. This was modular, and I skipped the first one. There's another module that talks about what happens in compressible flows. And so you can use the same type of analysis, and particularly on the forcing, to see what looks the same in an incompressible and in a compressible flow, and what is causing, for example, acoustic radiation to the free stream, which has a very important effect for wind tunnel studies and noise in trying to deal with, say, hypersonic transition. The turbulent boundary layers on the wall are a nightmare for that, as they radiate noise that kicks off transition in a different regime than you would see in flight. So I would put those as the sort of opposite ends of the extreme. One is a very practical tool. The other is giving you an origin or a way to sort of characterize a diagnostic that is used for something else. So one is turbulence, one is other. But it's a very good question, and I remember somebody very well known asking that in a Navy review and said, well, this is great, but what's everyone doing with it? And everyone was like, don't say that to the program manager, because there's a lot still we feel to uncover and different ways to think about this problem. But what do you do with it is the engineering problem rather than the scientific one. Yeah.
So you said a lot about space-time.
Yeah.
Is that in contrast to like omega k space? Is that what you're referring to?
Well, let me be extremely careful. Omega k can mean different things to different people. I have an omega k, and that's the one that I care about, yeah. But if you're talking about for Rand's model-based things, it's not the same, no.
So what distinction are you drawing when you say space-time?
So really I'm talking about the locality in the physical domain that you would get from a structure that is constrained, right? That would be not compact in the Fourier domain, right? And what I've shown you here is compact in the Fourier domain because it's single kx, omega being temporal frequency in kz, and therefore it's distributed in the physical domain. So that's really the distinction. The coherence that I'm saying is simple, or simpler, is in the Fourier domain, and therefore it's not compact in the physical domain. Yeah.
Thanks, Beverley. So, as you rightly point out, a lot of the work with data-driven spectral methods have focused on identifying coherent structures from these complex flows, but have struggled to back out, things like these self-similar structures and the different speeds of convection. What are the opportunities in that field for trying to basically extract this information purely from data?
Yeah, that's a really good question, yeah. So there's some older stuff, and it came about actually for the calibration of an older technique called hot wire anemometry, where people would calibrate on a flying rig. So you would just fly with a certain speed downstream, right? So that's essentially some of the stuff I've shown here. I think it'd be extremely interesting to do that kind of thing. So not Lagrangian, but fixed wave speed type observations at high Reynolds number. So that's one thing I'm interested in sort of thinking about how to approach. Now, what would it get you? It would get you the coherence associated with a particular wave speed, which is actually quite hard to unpick with a Cartesian coordinate with the diagnostics or the simulations that you have. The question is then you have a range of wave speeds, and it's not a very efficient way to do this. So I guess one thing I said that, I didn't say, but was implied in the nonlinear part is over a reasonable window. So even though we think about the Fourier average, the averaging to get into the frequency domain as being on an infinite horizon, right? Actually, if I do a windowed Fourier analysis over a short time, I still end up with a forcing that must equal the response through that resolvent operator. So there's actually, just because you're solving the equations, I'm still solving the same equations if I'm careful with how I analyze it. So I think there's quite a bit that can be done. The thing that I like here is actually binning these things up. So it's coarse graining, but based on the wave speed. I think that hasn't been as explored as it could be. And again, I need to be careful because people look at a lot of different things, but this is a way that I'm interested in exploring it. As I said, this idea of modeling, understanding what you should model by wave speed, by its contribution to the response, is one I'm particularly interested in. But I think it's an open question because we can do a lot more things now. The other thing that I think will be quite meaningful for this sort of thing is the neuromorphic event type cameras. So thinking about how to deploy those to deal with space-time. So not recording everything, but recording perhaps trying to extract something with the right wave speed out of those. It's not a fully formed idea, but there are new things we can do. I think it's wide open, actually. Yeah. So I should say this is painful, right? Because you've got to get a long data series, get into the frequency domain. You certainly don't want to implement control based on the frequency, but the modeling seems to be amenable to it.
Are there any other questions, please?
Thanks for the talk. So I was wondering when you showed the images of all the resolvent modes, because they were so clean, it was really easy to see the symmetry in all of the modes. And so I'm wondering if you can give some more intuition as to where the symmetry arises, and if it's possible, for instance, in a data-driven discovery or modeling scenario to directly enforce that kind of symmetry.
To enforce the symmetry, yeah. Yeah, so, I mean, I think if we go back to the place that I showed you, the hairpin vortices, it becomes kind of obvious, right? So there's been a big debate in the literature about, if I look at a transitional flow, transitional boundary layer, I will see something as clean as this, right? I'll see these hairpins. As I go up in Reynolds number, I start to see something a bit more like this. It's messier. As you go up and up, so you're adding more scales, you see a cane or an arch. You never see the full hairpin. And so at the very best, something like this would be understood as a conditional average, like a statistical representation, right? I saw part of it and then I saw the other part of it, but the whole of it comes back together. So I don't think that that's really in question. Some people say, well, okay, do I ever see even those things at very high Reynolds number? And there's sort of evidence to suggest that you don't. But that makes a lot of sense when you've got thousands more of these modes moving over each other, right? I would not expect to see anything as coherent in the physical domain, but I would still have this sort of behavior for each mode in the Fourier domain. I forget what your specific question was. Sorry.
About the symmetries.
Oh, the symmetries. Yeah. So I think people would say that if I average enough, I would get a symmetric representation here because there's nothing to bias these flows, right? But the enough data can be a lot of data, especially when you're at very high Reynolds number. So I don't think people use the symmetries very much. Well, that's not fair, very much. I think we always assume that they're symmetric, but they're not really imposed in the data-driven piece. Even when we do this sort of, or the nonlinear piece or anything in the Fourier domain, it's never perfect, right, on the finite time horizon. So there we do try and enforce some kind of symmetries because we know the statistics come out that way. So I think that that's a really interesting question, is what, perhaps we could flip it around to say what should we be, or what could we be enforcing that we're not, that would help with some of this stuff. Yeah, good question, yeah.
I have maybe two questions and a suggestion.
Okay.
Or a third question with some potential suggestion. So the first question is, at the beginning, you showed the H function.
Yeah.
And it sounds like this is the modeling function you start from, and you get the picture on the left.
Yeah.
So how is the data used in any way to,
good question.
over time, improve that function?
Yeah, so that's a really good question. So there are many things that you can do there, and I did not describe them all. And there are people doing very creative things in that space. Let's go to this one. Right, so everything I've showed you kept the full nonlinear forcing over here and just the turbulent mean over here. In the limit, right, if you think about an eddy viscosity type forcing, I could write this as a function of linear, the left variables on the left-hand side. And so in some sense, I would also like to be able to just model this, wrap it over, and then I have an eigenvalue problem, right? The problem with that is what I was showing you, essentially. That modeling this is very difficult, and it's very difficult to write it in terms of a scale-independent function. It cannot be a scale-independent function. We know, I've shown you that this is a very complicated thing, right? So it cannot be scale-independent. However, people have tried to find the optimal eddy viscosity to capture the behavior of flows in the fewest resolvent modes, right? So that's a very legitimate way to think about the efficiency of the basis set when you take a data set and you project it onto the basis. So trying to reduce the number of functions that you need. That's a good way to do it. The reason we don't do that here is because any time I mess with this forcing, all of these resonances and the simplification on the nonlinearity I was showing you goes away, right? Anything that's left over here is extremely complicated and very hard to interpret. So because we're interested in compressing the nonlinear term and improving that modeling, we keep it. But there's everything in between, right? How would I treat this to pull it over? Or in that U, as I said, like for the quasi-linear thing, I could bring stuff into that mean field, if you like. There's a very nice example of harmonic resolvent where if you have a single frequency, like an airfoil that's shedding periodically, you put that periodic flow into the mean, right? So that's now in H. I've got the space-time mean and a single frequency. It turns out that H becomes much harder to compute, or at least the inverse is much harder to do. But now you've put some information that would have been on the right in this basic analysis into the left, right? And so you get closer, you get better information, right? You get coupling now between that one frequency and other modes. So again, the nonlinear information is different. In the limit, what I said at the beginning is everything is correctly taken care of on the left, right? I've wrapped everything over on the left, and there's nothing to model anymore. So there's all flavors in between. It depends what your goal is. If you're trying to project onto a basis set, you want to make that the most efficient basis set. If you're trying to understand what drives what, maybe you keep it separate.
Okay. And now from the modes that you showed us, is it possible to recover things like average statistics, like the Reynolds stresses, where the profiles are reproduced with a certain level?
Yeah, so well, that's sort of a holy grail, right? So yes, if you get this right, okay, and so if you look at just spectra, you're only interested in the magnitude of these coefficients. If you look at 2-point correlations, you're interested in the complex magnitude or complex behavior of this. And so you need a way to approximate that chi to get to statistics, because again, an average in the physical domain will be an average over all the modes, right? So I have to have all the modes correctly weighted to do that kind of thing.
I see.
There might be, in answer to the other question, there might be something funky you can do in the middle there, where you're only looking at a subset and their relationship. Yeah, but to get to anything that is quantitative, I need to deal with those chi's. Yeah.
Okay, so now the question suggestion is, because I'm reminded of the work of Kida and Tanaka when we are showing inclined structures. Things in homogeneous shear turbulence are easier because you don't have the wall, and you don't have these issues of the scales and getting closer to the wall and whatnot. And also the mean profile of velocity is just a linear profile. So for example, in this paper by Kida and Tanaka in the 80s, they were able to find, through the analysis of vorticity equation, the inclination of the vertical structures. So I'm wondering about the use of this type of analysis in a simpler flow setting like homogeneous shear turbulence to see the understanding there before bringing it to, or, how that could help.
Yeah, so the key thing is you have to have shear, otherwise you lose this spatial localization that I was talking about, right? So homogeneous shear, yes. Homogeneous isotropic turbulence, I would say, is not the right question. So yes, and it's usually periodic, so that's a good thing too. I think my interest in this, in starting down this route, was to understand this engineering phenomenon, right? People have used we've looked at different flows. People use it for all sorts of flows now. In terms of the nonlinear term, I think that would be a potentially good test case. The reason I'm hesitating is these coherences that I've shown you, or these features that I've shown you, are hints to where you can compress or where things are important, right? And you see them in the spectra, we see them in the statistics, right? So as soon as I take away any of those features, I almost certainly have to keep all scales. You see what I mean, right? Although it's hard because there are these features that actually give us a way to compress information. We know those are important scales, and we can base off of some of these things. So it would be interesting to see how it came out. I probably could close things more easily, but I would need a lot of modes.
Right, there could be aspects of recovering the statistics, for the production and the Reynolds stresses that one gets, and say get these coefficients, and that would be applicable, for example, to the log layer, where... Yeah,
so there's one other thing that we'll talk about a little bit at APS that I didn't talk about here, is these very large-scale motions. There are some analytical things you can say about these that make them... I haven't got the right analogy. It's either the aorta or the tree trunk or the thing that actually controls spatial transport and spectral transfer. These rules are governed by these energetic, very large-scale motions. And so, again, that gives you it gives you where to start, whereas maybe you just have to look harder, but then have an easier time closing it. So I think that's a very valuable question. Yeah.
All right.
Good.
If there are no
Oh,
more
gosh.
questions, let's thank
Right,
Beverley
yeah,
one more
thank
time.
you. Lots of questions. Good.
Oh, and before we end, please.